Okay, to motivate Morera's theorem, let me first point out that triangles are star-shaped, not surprising. And so if I have a function that's analytic in a neighborhood of a solid triangle, so there's some domain containing this triangle, and let's label its vertices. Then the integral of f dz over the boundary of that triangle is 0, and often you have to talk about orientations and stuff like that with triangles or domains, but here I'll just tell you what I mean so we don't have to worry about defining orientations. I'll just say it's the line segment from z0 to z1 followed by z1 to z2 followed by z2 to z0. So no big deal. If I have an analytic function, then its integral around the boundary of a triangle will be 0. But here's a converse. So Morera's theorem says that if I have f, which is just assumed to be continuous, and if its line integral around the boundaries of triangles is 0 for every triangle in our domain, then f is analytic. So this theorem is nice because you can use it to prove all kinds of things are analytic. I think it's a little overrated because you can also equally well use Koshis theorem on circles to do usually what you do with Morera's theorem. So for example, a common corollary of Morera's theorem is that a local uniform limit of analytic functions is analytic. And we already proved this using, I guess, Cauchy integral formula on circles by passing a limit inside an integral. And you do basically the same thing with this integral of triangles. It's a little more conceptually efficient, but it doesn't have huge advantages. But in any case, people studying complex analysis should be familiar with it. A common corollary of it is something like this. If I have a function f defined on, let's say, an interval crossed with a domain in C, so we'll assume it's continuous on the product set, and that for fixed t, z maps to f of t comma z is analytic, then if I integrate this function from 0 to 1, the resulting function of z will be analytic. And so the proof is, well, you'd use some standard theorem. Because of the joint continuity, you get that this integral is automatically continuous. So you do have to check that in Morera's theorem. And then you'd integrate this on a triangle in the domain, but then you'd use Fubini's theorem to switch the two integrals, and then the integral of big F over this triangle will have to be 0 because big F is analytic. And then this would prove that F is analytic. So this is nice because it shows that certain functions are analytic. Let me give you an example of a famous function that you can show as analytic using this result, and then we'll get back to the proof of Morera's theorem. So here is the gamma function. It's defined as an improper Riemann integral of e to the minus t times t to the z minus 1, which since t is real, we would just view it as this, e to the z minus 1 times natural log of t. And it turns out the inside, or the integral, is absolutely convergent for a real part of z positive, because the inside in modulus is just this. And you can show that for x positive, this is finite. Okay, but this does not exactly fit the hypotheses of what we had over there because we have an infinite interval. If you had a better version of Fubini's theorem, you could fix that, but since we're not assuming that, you can sort of rig it to work by defining these approximations. I'll do my integral from epsilon to 1 over epsilon and try to send epsilon to 0. So this is a slight modification of the previous corollary. So the inside is analytic and continuous in t, or analytic in z and continuous in t and z together. And so this function is analytic by our corollary to Morera's theorem. But we can show that these truncations tend to gamma locally uniformly, and then that would show that gamma is analytic on this domain for real part of z greater than 0. So I can fix x naught positive and then look at real part of z between x naught and x1, which are fixed, and just estimate these terms. And so this integral from 0 to epsilon can be bounded for epsilon small by just the integral from 0 to epsilon of t to the x minus 1. And I don't want to go through the details, but you can bound it by something that goes to 0 as epsilon goes to 0, independent of x, as long as x is trapped between these two fixed values. And you can do something similar with the rest of the integral from 1 over epsilon to infinity. And again, I don't want to go too much into the details, but you get bounds on these so that you have, so that this difference goes to 0 locally uniformly. And so then you'd get that gamma is a local uniform limit of things we know to be analytic. And so we get that the gamma function is analytic out of Morera's theorem. Okay, so now let's quickly show how to prove Morera's theorem. Okay, so the problem is local. So we can assume our domain is just the unit disk for simplicity. Okay, and this is similar to how we, something we did in simply connected domains. I'll define f of z is the integral of f on this interval from, or say line segment from 0 to z. Okay, now fix a z naught where we're going to try to compute the derivative of capital F. Now our hypothesis is that the integral on these triangles is 0. So the triangle going from 0 to z naught, and then z naught to z, and then z back to 0, the integral along that will give me 0. But this first part here is f of z naught. This part is negative f of z. And so we get that f of z minus f of z naught, and we're trying to compare that to little f of z naught times this difference to show that this derivative is little f at z naught. This difference here will be just this integral of little f along the line segment. On the other hand, I can just integrate this constant function on the line segment to get this difference of values, z minus z naught. So I'm just using this fact. and bringing f inside the integral. And so now I can bound this by doing supremum of the inside times the length of the path. And this part here, I can control and make that small by making z sufficiently close to z naught, just using continuity of little f. And then that gives me the power to make this. That's how I can show that this is little o of z minus z naught. And out of this, we get that the derivative at z naught is little f. So capital F is an antiderivative of little f. So capital F is analytic. But then derivatives of analytic functions are analytic. So little f is analytic. And notice we started just with a continuity assumption of f and this property of integrals over triangles being 0, and we deduced that little f is analytic.